Hello, I'm going to talk about sharp threshold results for computational complexity. This is joint work with Lijie Chen and Ryan Williams from MIT. In complexity theory, we want to prove lower bounds. Currently, we know how to prove some weak lower bounds. For example, we can show some explicit language that requires cubic size De Morgan formulas. But actually, we believe that much stronger lower bounds hold. For example, we believe that NP is not in NC1. But we still don't know how to prove such strong lower bounds, and there are some formal complexity barriers from proving them using current techniques. So we are still far away from proving strong lower bounds. Now we want to ask the following question: can we quantify how far we are from various open lower bounds? Heuristically, we are closer to an n to the 3.01 formula lower bound than NP not in NC1. Both of these are open problems, but the first one only requires a small improvement on the current best result, while the second one is a super polynomial size formula lower bound, which seems to be much harder than the first one. However, this intuition can be wrong. A recent line of research studies a strange phenomenon called hardness magnification. It shows that some weak lower bounds are as hard to prove as strong lower bounds. So it's actually quite hard to estimate the difficulty of proving lower bounds. In this paper, we show some more extreme magnification theorems, which we call sharp thresholds for complexity theory. Okay, first let's look at a problem which is closely related to hardness magnification. It's called minimum circuit size problem, or MCSP for short. In the MCSP problem with the circuit size parameter S of m, we are given as input the truth table of an m variable Boolean function f, and we want to decide whether f has a circuit of size at most S of m. It's clear that MCSP is an NP language. A witness is just a small circuit that can compute the language correctly. And we can easily solve the MCSP problem in n times 2 to the S of m time by an exhaustive search over all the possible circuits. However, we don't know how to improve this trivial algorithm. In fact, under cryptographic assumptions, MCSP m to the 10th is not in P/poly, because otherwise we could use it to break strong PRGs. So we believe that MCSP is a hard problem. A recent theorem by McKay, Murray, and Williams shows that if we could prove a slightly superlinear size circuit lower bound for MCSP problem, then it would imply NP is not in P/poly, which is a breakthrough lower bound. This kind of theorem is called hardness magnification. It magnifies a weak lower bound into a strong lower bound. And there has been a lot of research along this line. For example, if we could show that approximating max clique requires superlinear size circuits, then it would also imply NP is not in P/poly. And there are many other similar results which apply to different kinds of languages. Okay, so how do we view hardness magnification? As we mentioned before, it indicates that proving weak lower bounds is harder than we previously thought. Previously, we knew that proving strong lower bounds is hard, but now we know that proving some weak lower bounds is as hard as proving strong lower bounds. So this is a pessimistic view. On the other hand, an optimist would say that hardness magnification suggests some new approaches to proving strong lower bounds. We could first prove some weak lower bounds, perhaps using techniques that we are familiar with, and then we could apply hardness magnification to obtain some strong lower bounds. In fact, it is argued that this kind of approach can bypass the natural proof barrier by Rozborov and Rodich. However, a recent result formulated a new barrier called the locality barrier, which we have to overcome before we could use hardness magnification to get strong lower bounds. Now let's look at some previous hardness magnification theorems. In this theorem, it is required to prove an n times polylog n size circuit lower bound for MCSP. Let's compare it with the lower bound that we know how to prove. First, there is a trivial circuit lower bound of n-1, simply because the MCSP language has to depend on all the input bits. However, our progress in improving this trivial bound is still quite limited. Currently, the best circuit lower bound is only better by a constant factor. But if we want to apply the magnification theorem, we have to improve it by a polylog n factor. So we are still far away from reaching that magnification threshold. Here is another example. This theorem requires to prove a slightly supercubic size formula lower bound for MCSP m to the 10th. For this language, currently the best lower bound is slightly subquadratic. It is much better than the trivial bound, but it still has a large n to the 1 plus epsilon gap from the magnification threshold. Now I'll describe our new results. We show hardness magnification theorems with sharp thresholds, while the magnification thresholds in previous works were not sharp. By sharp, we mean the following. First, we can prove a lower bound of n to the c for some language L, and this lower bound is much better than the trivial bound, so c had better be strictly greater than 1. Second, we show that if we could improve this exponent c by any positive epsilon for this language L, then it would imply a breakthrough lower bound. We also show magnification results for other tasks. We not only can magnify lower bounds, but can also magnify quantify the randomization and explicit obstructions. This is a new definition in our paper, and we'll see later. And these magnification results also have sharp thresholds. So if we could improve the current results by a little bit, then it will also imply breakthrough lower bounds. And we remark that these approaches for getting strong lower bounds are not ruled out by the reason locality barrier. Now I'll describe each of our results in detail. In the following, we'll mainly work with formulas. And by formulas, we always mean De Morgan formulas. First, we show hardness magnification for probabilistic formulas. A probabilistic formula is just a distribution over formulas such that for any input, if we draw a random formula from that distribution, then it computes the correct answer with probability at least 2/3. And the size of a probabilistic formula is just the size of the largest formula from the support. We show that if we could prove that MCSP m to the 10th doesn't have n squared times polylog n size probabilistic formulas, then it would imply P space is not in NC1. This magnification threshold is sharp because we can prove a slightly subquadratic lower bound for the same language against probabilistic formulas. We remark that there are cubic size lower bound against probabilistic formulas for the dense version of MCSP, which has a much larger size parameter. But this cubic lower bound is not sufficient for hardness magnification, because so far we only know how to do magnification with the sparse version of MCSP. Next, we consider the quantify the randomization problem, first introduced by Goldreich and Wigderson. In this problem, we are given a circuit, and we are guaranteed that this circuit accepts most of the input strings. It only rejects at most B of n inputs, where B of n is a very small parameter. And we want to deterministically find an input string that is accepted by this circuit. And our algorithm should run faster than exhaustive search. In the standard setting, we want to do a full de-randomization. So the parameter B of m is 1/3 times 2 to the m. But this problem is very hard, and we don't know how to do it even for very restricted circuit classes. So we consider an easier version, the quantify the randomization, where the parameter B of n is only 2 to the n to the alpha for some alpha strictly smaller than 1. There has been a lot of research on quantified randomization and its relation to full randomization. And many circuit classes were studied, such as AC0, TC0, and A0 mod 2. In this paper, we study quantified randomization of probabilistic formulas. First, we show a polynomial time quantified randomization algorithm for probabilistic formulas of size n to the 2 minus alpha minus epsilon for any positive epsilon. Then we show that if we could design a similar algorithm for a generalized version of probabilistic formulas of slightly larger size, then it would imply full de-randomization of all polynomial size formulas in polynomial time. Here we omitted the technical definition of generalized probabilistic formulas. In this generalized setting, we also have a quantified randomization algorithm, although the size that we can achieve is smaller. Next, we consider explicit obstruction against formulas, or we can call it explicit proofs of formula lower bounds. An explicit obstruction against S of n size formulas is a deterministic poly n time algorithm that can print a list of input-output pairs such that every formula of size at most S of n is inconsistent with at least one of the pairs in the list. This can be seen as an explicit proof that some poly n time function does not have S of n size formulas. This is inspired by Momoli's notion of explicit obstructions from his GCT program. He argues that in order to prove strong lower bounds, we should try to find explicit obstructions against small circuits. We know that the parity function requires formulas of n squared size. Our first theorem is an explicit proof of this lower bound with a small loss in the formula size. However, we know that the best known formula lower bound is nearly cubic. So can we make the proof also explicit? Or can we even show an explicit proof of a slightly superquadratic formula lower bound? Our second theorem says if we could do that, then it will imply breakthrough lower bound. First, it implies E, which is deterministic 2 to the order n time, has no 2 to the little of n size formulas. Second, it implies explicit obstructions against n to the k size formulas for all k. In fact, these statements are equivalent. To summarize, we have considered 3 different tasks, and for each of them, we show a slightly subquadratic result and a magnification theorem with sharp threshold. Now let's look at our proof techniques. For the first 2 magnification theorems, we adapt the result from previous works. Our proof techniques are similar, but we are looking at different computational models. Instead of looking at circuits or formulas, we look at probabilistic formulas, which allow us to get sharp thresholds. For the magnification theorem of explicit obstructions, our proof uses efficient linear hashing. Now let's look at the proof sketch. Suppose we have an explicit obstruction against n to the 2 plus epsilon size formulas, which is an algorithm that can print a list of pairs, xi and f of xi. We want to show that it implies exponential size lower bounds for E. We want to prove a contradiction, so let's assume that E has 2 to the little of n size formulas. First, let's pick a linear hash function h, which can map all the input strings from the list into distinct hash values. There are only poly n many strings in the list, so we can make the hash values have length log n, and the seed that describes the hash function also has log n bits. Such a hash function can be found deterministically in polynomial time by simply trying all the possible seeds. Then we construct an algorithm A. It receives a hash value as input, and then it goes through all the strings in the list and finds the unique string xi, which has the same hash value. and then it outputs the correct answer, f of xi. The algorithm A runs in deterministic polynomial time, and it has input length log n. So by our assumption, it has n to the little of n size formulas. Then we compose A with the formulas that compute every bit of the hash values, which is a parity function. So each of these formulas has n squared size. Now we get a formula that can correctly solve all the input strings from the list, but its size is smaller than n to the 2 plus epsilon. So it's a contradiction to the definition of explicit obstructions. So our assumption is false. Now let's look at our proof techniques of the slightly subquadratic results. For all of these three results, the technical ingredient is the same, which is a de-randomized version of Hastad's shrinkage theorem. Now let's look at this result. First, we have some definitions. A restriction is a function rho which maps from all the n input coordinates into 0, 1, and star. If rho of I is 0 or 1, then it means that we fix the ith input bit to 0 or 1. And if rho of I is a star, then it means that we don't fix the ith input bit. Given a Boolean function f with n input bits, we can apply rho to f and obtain a restricted function, which can usually be much simpler than the original function f. As an example, let's see how a restriction could simplify a formula. Here we have a formula of size 4, and it has 3 input bits. Let's apply restriction rho, which fixes the first input bit to 0, and the other 2 input bits are not fixed. Under this restriction, the left subtree of this formula gets killed, and we can easily see that the output of this formula only depends on x3. So the restriction rho simplifies f into a formula of size 1. Usually, we consider the expected shrinkage under random restrictions. Let's look at the definition. For a parameter p between 0 and 1, in a truly random p-regular restriction, all the input coordinates are independent. For each of the input bits, with probability p, we leave it unrestricted, and otherwise, we fix it to 0 or 1 with equal probability. There is a famous shrinkage theorem proved by Hastad and later improved by Tao, which says that a truly random p-regular restriction shrinks a formula by an order p-squared factor in expectation. This is an important theorem and is very useful in proving formula lower bounds. Here we notice that in order to sample a truly random restriction, it requires a linear number of random bits. Our main technical contribution is a de-randomized version of this shrinkage theorem. We construct a pseudo-random restriction generator which can sample a restriction using only log n random bits in polynomial time, and the shrinkage property is almost preserved. It can shrink a formula by roughly a p-squared factor with only a small loss in the formula size, and is close to p-regular. With constant probability, at least p/2 fraction of the n input bits are unrestricted. This is slightly weaker than being exactly p-regular, but it's sufficient for our applications. We remark that our log n seed length is optimal and improves the previous log squared n seed length by Oliveira, Peak, and Santner. Our proof technique uses a more refined version of the iterated pseudo-random restriction method. Our log n seed pseudo-random restriction immediately implies these 3 results that we have claimed. As an example, let's see one of the implications. We'll show an explicit proof of the parity lower bound against slightly subquadratic size formulas. Let's first apply our restriction generator with parameter p set to 10 over n. Our restriction has log n seeds, so there are only poly n many possible restrictions printed by our generator. Now, for each of these restrictions, we add two input-output pairs into our list. We first pick an arbitrary coordinate that contains a star, and in one of these two strings, we set it to 0, and in the other string, we set it to 1. And for all the remaining stars, we set them to zeros. So we get two strings which differ by only one coordinate. So they have different parities. Now let's look at any formula f of sub-quadratic size, and we know that our restriction generator can simplify a formula by roughly a p-squared factor. So we can show that there exists a row printed by our generator such that under row, the formula f shrinks to the trivial formula of size 0. So it can only output a constant value. And there exists at least one star in the restriction row. Now let's look at these two strings derived from this particular row. We know that f should output the same value on these two strings because f is a trivial formula. But these two strings have different parities. So we know that f is wrong on one of them. So this is an explicit proof that f cannot compute parity. We conclude with some open problems. First, can we construct an explicit obstruction against n to the 2.01 size formulas? Of course, this could be very hard because it would imply breakthrough lower bound. So we want to ask, are there any formal barriers? Second, does our log seed pseudo-random restriction generator have other applications? Thank you for listening.